In this video, we're going to continue finding the volume of three-dimensional objects that are created when two-dimensional regions are rotated or revolved around an axis. The difference between these solids and the ones that we looked at in our last video is that there is going to be space between the region of area and the axis of revolution. So if you look with me at this two-dimensional graph here, the shaded region is above the axis of revolution that's going to go around the x-axis. So when we revolve that, the space here between the region and the axis creates a hole or an empty space in our three-dimensional shape. And when we cross-section that, we're still going to get circular cross-sections because of the revolution, but we're also going to get these circular holes, which are not part of the volume that we're trying to find. So we're going to need to subtract those out. So we'll still find the volume of the circular cross-sections, but then we'll have to subtract out the volume of the circular hole cross-sections. And just so you know, these cross-sections that have a hole in them are often referred to as washers, where the ones that were solid in our last video, those are referred to as disks. You'll notice that for the cross-section area, I used a capital R, and that's going to be the larger radius of the solid figure as it revolves around the axis. And the cross-section of the hole, I used a lowercase r, and that will be the radius of the empty space as it revolves around the axis. And please know that we'll look at both horizontal axis of revolution and vertical. And so those will create either dx or dy integrals as we've seen in the past. In this first example, we'll look at the region bounded by these two functions revolved around the x-axis. So I drew in my axis of revolution arrow. We have a nice two-dimensional graph as well as a three-dimensional rendering of what that would look like when it's revolved 360 degrees. And again, I'll mention that you are not given these visuals on the AP exam. At most, you'll be given a two-dimensional graph. So it might be worth a quick Google search to look at some videos or simulations of how this volume is created, just to give you a better idea of what we're looking at. So let's start by looking at the setup of our thinking. Again, we always go back to volume is the integral of area. It is a dx integral because we're going around the x-axis. And when I looked at the two-dimensional shape, I saw that there's space between that region and the x-axis, And so I knew to set up a big pi r squared minus a little pi r squared for the whole. And let's go about finding those big R and little r expressions, as well as the limits for our dx integrals. Starting with the limits, I had to figure out where my two functions intersect. And so before I could do that, I wanted to solve this one for y equals, so I had to square root both sides. I got square root of 8x. And then I set the two equations equal to each other. I squared both sides, subtracted the 8x, factored out the x, and when I set both factors equal to 0, I got 0 and 2 for my limits. So the lower limit is 0 for both integrals, and the upper limit is 2. The big R, or the radius of the larger object, is created by the function that revolves around the x-axis. And I haven't quite drawn the point all the way to where I should have. So that is controlled by the greater function, or the top function here. And it looks like it's labeled as the square root of 8 function. So that's what we'll put in for our big R. And then the radius of the whole, or little r, is controlled by that lesser function that's on the bottom, and that is our x squared parabola function. So we'll put that in for little r. Since these limits are nice whole numbers and these functions are easily squared, you can imagine this would be a problem that we would do without the calculator. So I went ahead and squared the two functions before I find my antiderivatives. I found the antiderivatives to be 4x squared for the first term and x to the 5th over 5, just using the power rule for both. And now I'll use my fundamental theorem of calculus and plug in my limits and subtract. So my upper and lower limits plugged in for the first antiderivative gave me 16 minus 0. For the second, 32/5 minus 0. And I'll remind you that you can leave this answer as soon as you plug in your limits, and you'll get full credit for that answer on an FRQ. But if you're a multiple choice, you would have to go ahead and simplify and combine to get your final answer of 48 fifths pi. And just one more visual hint that I gave in the last video but didn't mention today yet. If we don't have that three-dimensional figure, it may help you to draw that symmetric region as it's rotated about the x-axis to give you a better idea of what the three-dimensional figure looks like. I'd like to do one more example of a washer, and this one is different for two reasons. First, it's going to go around a vertical axis instead of horizontal. And the second is that vertical axis is not the y-axis. They have shifted it to the line x equals -1. So we'll talk about how those two things affect our integrals as we set it up. So volume is still the integral of area. We're going to choose dy because we have a vertical axis. So even though it's not the y-axis, you can think about it being parallel to the y-axis, and that gives us the dy. I can see that I have space between my shaded region and my axis of revolution as it goes around that. So I'm going to have a washer situation. So pi big R squared minus pi little r squared. And so my job now is to find some limits for my dy integrals as well as expressions for the big R and little r. For my limits, they need to be y values. So if you look at your shaded region, it spans from -2 to 2 on the y-axis. The larger radius, or big R, is controlled by this semicircular function, which is given as the square root of 4 minus y squared. And that is revolved around this axis of x equals -1. So I need to find the distance between my function and the axis of revolution. And so instead of top minus bottom, which we do in a horizontal situation, when we have a vertical axis, we have to do right minus left, because that's the greater function minus the lesser. So it'll be my square root function minus my axis of revolution, which is -1. So that's going to create a plus when we put it into our integral. So we have our function square root of 4 minus y squared minus, because we're finding the distance or the difference between the two functions, -1, which is our axis of revolution. So as soon as you see that double negative, you're welcome to make that a big plus. You can leave it as a double negative. They're both mathematically correct, so it's more of a preference thing. To find the smaller radius, or the radius of the empty space or the hole, we would go from the y-axis to our axis of revolution, which is x equals -1. And so remember that our y-axis is really the same function as x equals 0. So to go from right minus left, I have to do 0 minus the axis of revolution, which is -1. And of course, that gives us a 0 plus 1, or just 1. And that radius is a lot of times easier to see visually, that it's just a unit of +1. This question would most likely be a calculator evaluation. So remember, you have two options. If you do not type the pi in with your Math 9, you'd have to include it in your answer. So it'd be 23.233 pi. If you type the pi's right into your Math 9, or right in front of the Math 9s, you should get a final answer of 72.989 for your volume. I just quickly wanted to show you one more example that's slightly different, because we are going around a horizontal line, y equals 2, and that axis of revolution happens to be above our shaded region, and we hadn't seen one quite like that before. So in this one, we have to write or set up but do not evaluate our integral. We've got a dx because it's a horizontal axis. Our limits are from 0 to 2. And forgive me, that's actually 0 to 4. Common mistake to pick the y value instead of the x, but I corrected it. So 0 to 4 on the x-axis. Our shaded region goes from 0 to 4. And then to find our big R and little r, this is the difference we haven't seen. We need to find the distance between our axis of revolution and our functions. So you start with the top, which is 2 minus the bottom function. So for big R, it's 2 minus that linear function x over 2. And for little r, the space between of our radius of our hole would be 2 minus square root of x. So just stick with that concept of top minus bottom to find that distance. And we've seen that concept throughout this unit. So we'll definitely practice some more examples when we get back together.